Assalamualaikum, and today we will be presenting about infrared radio technology. But first, these are the group members for the presentation. Now, what is infrared technology? So, infrared technology is actually based on infrared radiation, which is a type of electromagnetic radiation that is located between visible light and microwaves in the electromagnetic spectrum. Even though the human eye cannot see the radiation, it can be detected as heat because all objects emit infrared radiation. This technology can be used to detect, measure, and analyze temperature without direct contact. So that made infrared technology an important tool in many modern applications, such as thermal imaging, night vision, and temperature sensing. Infrared radiation can also be used in short-range wireless communications, such as in TV remote controls. Because of its ability to detect heat and operate in low-light conditions, infrared technology has become an essential tool in many scientific, industrial, and everyday applications. To understand more about infrared technology, we need to look at the three important scientific principles. First, infrared radiation is one of the electromagnetic spectrum. It is located between visible light and microwaves. The wavelength of infrared radiation is around 780 nanometers to 1 millimeter. When the wavelength of infrared radiation is longer than visible light, infrared radiation cannot be seen by the human eye. Second, infrared technology is based on the thermal radiation. So every object with a temperature above absolute zero will emit infrared radiation. The amount of radiation emitted depends on the object's temperature. So for better understanding, hotter objects will emit more infrared radiation than cooler objects. Third, infrared sensors are able to detect these emitted infrared wavelengths. When infrared radiation reaches the sensor, it is converted into electrical signals. Then, these signals are processed and displayed as useful information such as temperature readings and thermal images.
Now, I will explain about the scientific principle of the thermography and thermal imaging technology. Thermography is a technique that uses infrared radiation to detect heat emitted by objects. Infrared radiation is part of the electromagnetic spectrum and cannot be seen by the human eye. Since all objects above absolute zero emit infrared energy, thermal cameras can capture this energy and convert it into visible image that show temperature differences. Unlike ordinary cameras that capture visible light, thermal imaging cameras detect infrared radiation emitted by objects. Since all objects above absolute zero emit heat energy, the camera can measure this radiation without making physical contact. The infrared radiation passes through a special lens and is detected by an infrared sensor called a microbolometer. The sensor converts the heat energy into electrical signals, which are then processed by the camera's software. The software assigns different colors to different temperature levels. Hotter areas usually appears red, orange, or white, while cooler areas appear blue or purple. The final image produced is called a thermogram, which allows users to easily identify temperature differences that are invisible to the human eye. Thermography has many practical applications. In healthcare, thermal cameras are used for fever screening because they can measure temperature without physical contact. In industry, thermography helps detect overheating electrical equipment before breakdowns occur. In buildings, thermal imaging identifies heat loss and insulation problems, helping to improve energy efficiency and reduce costs. For my final explanation about the thermography provides many advantages, including non-contact temperature measurement, real-time monitoring, and improved safety. However, Thermal cameras can be expensive and require trained personnel to interpret the images accurately. In conclusion, thermography is an important application of infrared radiation technology that is widely used in medicine, industry, and building inspections to improve safety, efficiency, and early problem detection.
Now, let us shift our attention to a second highly critical practical application in the world of modern scientific instrumentation, night vision technology. As we all know, human eyes have a biological limitation that prevent us from seeing in a pitch black condition. However, through the application of infrared physics, this limitation have been successfully overcome. It is important to note that night vision devices do not magically create light. Instead, they detect electromagnetic infrared waves that exist just beyond the spectrum of human visible light. Let's dive deeper into the scientific instrumentation behind these devices. The most popular system used in defense sector today is known the image enhancement. How exactly does it work? When magnetic rays of ambient light, such as starlight or moonlight, enter the device, this light particle or photon are converted into electron by a sensitive layer called the photocathode. Next, this electron pass through the most critical component of the device, the microchannel palette or MCP. The MCP is a microscope disc containing millions of tiny glass tubes that are intentionally tightened at a slight angle. This is where a fascinating physics phenomenon occurs, known as secondary emission. Where the high voltage is applied across the plate and incoming electrons strike the inner wall of the tube. This high energy impact forces the wall to release multiple secondary electrons. As these electrons travel down the tube, they repeatedly strike the walls in a cascading domino effect. As a result, a single entering electron is exponentially multiplied into thousands. At the end of the tube, this massive flood of electrons hits a phosphorus screen, creating the bright, well-defined green image that user sees. In addition to the green tinted image intensifier technology, another major branch of infrared night instrumentation is thermal imaging. The key difference here is that thermal imaging requires absolutely no ambient light to operate. It functions entirely on the principle that any object with a temperature above absolute zero emits thermal infrared radiation, specifically in the far infrared spectrum. The specialized lens of the device typically made of germanium because standard glass block infrared light focuses this radiation onto an array of detectors. This system constructs a digital temperature map called a thermograph. This allows operators to easily detect warm bodies, vehicles, or structures even through thick fog, smoke, or total camouflage. In the real world, the implementation of this scientific instrumentation is incredibly fast. Firstly, it is widely deployed by defense forces for covert tactical operation at night. Second, it plays a life-saving role in search and rescue missions, where helicopters utilize thermal cameras to spot the heat signature of a missing person in dense forests or open water at night. Furthermore, wildlife biology relies on passive infrared devices to monitor nocturnal animal behavior without disturbing their natural habitats, massively utilized daily through standard infrared home security system. In conclusion, night vision instrumentation beautifully demonstrates how physics theories of electromagnetic waves and secondary emission are bridged together to create real-world technologies that protect lives and enhance global security.
Now, I will explain how infrared or IR technology is used in environmental monitoring and remote sensing. Infrared technology detects thermal radiation, which is heat emitted by all objects. Since every object above absolute zero emits infrared radiation, IR sensors can measure temperature and identify environmental change without direct contact. IR sensors are commonly mounted on satellites, aircraft, and drones. These sensors collect thermal data from the Earth's surface and atmosphere. The information gathered helps scientists monitor weather patterns, climate change, vegetation health, ocean temperatures, and pollution levels. As a result, IR technology plays an important role in understanding and protecting our environment. Next, let's look at some real-world applications of infrared technology. First, satellite weather tracking. Weather satellites use infrared cameras to monitor cloud temperature and movement. This helps meteorologists track hurricanes, thunderstorms, and monsoon systems, improving weather forecasts. Second, gas leak detection. Infrared sensors can detect and locate leaks of methane, carbon dioxide, and other industrial gases. Oil and gas companies use infrared camera to identify gas leaks in pipelines and processing plants, helping to improve safety and reduce environmental damage. Third, measuring greenhouse gas concentrations. Satellites equipped with infrared spectrometers measure how much infrared radiation is absorbed in the atmosphere. This allows scientists to monitor global carbon dioxide levels and support climate research and environmental policy planning. These applications show how infrared technology contributes to environmental monitoring and help us address environmental challenges. Now, we'll talk about the benefits of environmental monitoring and remote sensing. First, remote sensing serves as our global early detection system, shifting our strategy from reacting after a disaster happens to predicting it before it strikes. By identifying subtle anomalies, such as rising thermal hotspots before a wildfire breaks out or tracking early atmospheric shift before severe weather events. This technology buys us invaluable time in emergencies. This extra time translates directly into save lives and protect communities. Second, this technology enables completely safe, non-invasive data collection. Historically, gathering high-fidelity environmental data meant putting human life in harm's way. Today, scientists and inspectors no longer need to be exposed to dangerous conditions, such as toxic gas leaks, extreme weather, or active volcanic eruptions, because remote sensors can gather precise, critical data from a safe distance. Finally, we now have access to continuous large-scale global coverage. Unlike other visible light sensors that depend entirely on daylight, modern satellites utilize infrared sensors to detect thermal radiation. This means we are never blind when the sun goes down, allowing us to track massive storm systems, cloud formations, and changing weather patterns uninterrupted through the night. Together, these tools redefine how we protect, understand, and sustain our world.
So thank you, my friend. So we are moving into the technical backend and instrumentation engineering of our system. Let's look at how this device actually see invisible infrared radiation and turn it into data that we can use. The core of this process is signal conversion. When infrared radiation hits our instrument, it encounters a specialized detector. Depending on the application, we generally use one of two types. First, we have InGaAs or indium gallium arsenide detectors. These are quantum detectors. When an IR photon strikes this semiconductor material, it directly excites an electron, generating an instantaneous electrical current. They are incredibly fast and highly sensitive, making them perfect for near-infrared application. On the other hand, for long-wave thermal imaging, we often use microbolometers. They are thermal detectors. Instead of exciting electron directly, the incoming IR radiation slightly heats up a tiny suspended pixel structure. This temperature change alters the material's electrical resistance. Whether it's a change in current from an InGaAs sensor or a change in resistance from a bolometer, this raw analog signal is amplified, passes through a readout integrated circuit, and converted into a digital signal that our software can finally render as an image or data point. Moving to the next part, now, engineering an infrared instrument comes with a massive inherent challenge: noise control. Because infrared radiation is essentially heat, these sensors are highly susceptible to thermal interference, often caused by the device's own internal temperature. At room temperature, the atoms inside the detector materials are constantly vibrating. This thermal energy causes electrons to break free, even when no external light is hitting the sensor. This unwanted electrical signal is what we call dark current. In real-world terms, dark currents creates a massive amount of background noise, which completely blurs or makes or masks the actual IR signal we are trying to measure. To solve this and achieve high precision, we have to cool the sensor down to cryogenic temperatures, often as low as negative 196 Celsius. To do this without carrying around liquid nitrogen, advanced IR instruments integrated a mechanical cooling system called a Stirling cryocooler. The cryocooler uses a closed-cycle piston to compress and expand helium gas, moving heat away from the sensor. By physically freezing the detectors, we silence those atomic vibrations, virtually eliminate dark current, and get an ultra-crisp, accurate thermal reading. And finally, let's talk about calibration. An infrared instrument doesn't inherently know what a specific voltage or resistance readings means in terms of actual temperatures. It has to be taught And we do this by using a gold standard known as a blackbody source. In physics, an ideal blackbody is an object that absorbs all radiation and emits a perfect predictable spectrum of thermal energy based entirely on its temperature. In the engineering lab, we use commercial blackbody calibration cavities that can be set to exact highly stable temperatures. We point our IR instrument at the blackbody at several known intervals. For example, exactly 20 Celsius, 50 Celsius, and 100 Celsius. By mapping the sensor's electrical output against these perfect reference points, engineers create a precise calibration curve. This curve is programmed directly into the device software. This ensures that when an end user points the instrument at the real-world object, the internal data translates flawlessly into highly accurate temperature measurement.
Alright, Assalamualaikum warahmatullahi wabarakatuh. My name is DANISH QASHRI and I will be presenting on benefits on infrared technology, challenges and limitations, future trends, and lastly, our conclusion for all of us. So, infrared technology offers several important benefits. First, it allows non-contact temperature measurement, meaning the temperature of an object can be measured without physically touching it. This makes the process safer, faster, and more hygienic. For example, we can see this being used in clinics or when in our previous pandemic. Second, infrared system can operate effectively in darkness because, of course, they detect heat rather than visible light. This is especially useful for night vision and security application. Another benefit is the early fault detection. Thermal imaging can identify overheating electrical components or machinery before serious damage occurs. This is actually very useful for industrial and electrical machinery. Finally, infrared technology is widely used for environmental monitoring, such as detecting forest fires, monitoring pollution, and observing weather conditions. But despite its advantages, infrared technology also has several limitations. One common misconception is that infrared cameras can see through walls, as we can see in movies. But this actually, in reality, isn't true. They only detect heat emitted from surfaces. So another one, their performance can also be affected by environmental conditions such as fog, heavy rain, or smoke, which may interfere with infrared radiation. If I have to give an example, imagine infrared as a whole red screen, and then with these environmental conditions, we will never see through. Imagine it as a wall. Okay. So another limitation is cost. High quality thermal imaging equipment can be very expensive, making it less accessible for some users, especially us students. In addition, when objects have similar temperatures, it can become difficult for infrared system to distinguish between them accurately. I mean, they literally use heat to detect something. Alright, now I will talk about infrared's innovation. Their technology is very promising. One growing application is in smart homes, where infrared sensors can automatically control lighting, security system, and energy usage by detecting human presence. For example, we coming in a room and pop, open lights. Infrared technology is also becoming increasingly important in autonomous vehicles. Thermal cameras can help detect pedestrians, animals, and obstacles during nighttime driving, improving road safety. Another important development is in the integration of artificial intelligence. AI can analyze thermal images more quickly and accurately, helping industries identify faults or detect potential problems automatically. In addition, infrared sensors are becoming smaller, more affordable, and more energy efficient, allowing them to be integrated into smartphones, wearable devices, and other consumer products. Alright. To sum up what all of us just presented, Infrared technology plays an important role in many fields, including healthcare, security, environmental monitoring, and industrial inspection. Its ability to detect heat without direct contact makes it a valuable tool for improving safety, efficiency, and even monitoring capabilities. Although there are very lots of limitations such as equipment costs and environmental interference, ongoing technological advancement are helping to overcome these challenges. We should be proud with our engineers. With developments in artificial intelligence, smart home system, and autonomous vehicles, infrared technology is expected to become even more important in future. Alright, that's all from me. Thank you for listening.